First, I want to thank the organizers for inviting me to give a presentation in this nice conference. Today, I will tell you about a recent paper that I put out with Simon. As Shota said, N=4 super-Young Mills is our candidate to be the first solvable four-dimensional gauge theory. And a lot of progress has been done in this pursuit thanks to its special symmetries and dualities. In this talk, I will present a new hidden symmetry that appears in the context of correlation functions. And that will also allow me to define a new duality between correlators and massive amplitudes. First, let me start by stating an old duality that we will later generalize. So this is a 10-year-old duality between correlation functions of the smallest protected operators and a scattering amplitude of massless gluons in living in a dual space. The way to show this duality has two steps. So in the first step, we consider the null limit. We consider the points to be sequentially null separated. And in that limit, effectively, we have a fast particle propagating in this contour, and that gives rise to a Wilson loop. On the second step, we consider a duality that maps N=4 super-Young Mills to itself, but it changes the Wilson loop to a scattering amplitude. In terms of the kinematics, this is just can be simply stated as relating the momenta of the massless particles to be identical to the edges of the null polygonal Wilson loop. Now we would like to ask if we can come up with a generalization of this duality for the case of massive amplitudes. When we talk about massive amplitudes in N=4 super-Young Mills, we need to go to the Coulomb branch. So we turn on some expectation values for scalar fields and some fields acquire masses. So we can here consider the scattering of massive W bosons. And it was found that this amplitude satisfies a higher dimensional symmetry that acts on the vector composed by the momenta and the mass. So the masses are treated as extra dimensions under this higher dimensional symmetry. Of course, if we are looking for some correlator that satisfies a duality, we better have a candidate that can give rise to a higher dimensional structure. Those candidates are related to these BPS operators that are dual to Kaluza-Klein modes in ADS-phi cross S-phi. These operators are single trace operators, traces of, in this case, K products of fields parameterized by the four-dimensional space-time position and a six-dimensional polarization vector that has to be null for this operator to be protected. This extra six-dimensional polarization vector is the one that encodes, in the boundary theory, encodes the kinematics of the S-phi. It was found that in the regime of a strong coupling that is dual to supergravity, when we consider the sum of all the 4-point correlators of these BPS operators, there is we define a single object that has an emergent 10D symmetry. In this talk, I will present that there is a similar 10-dimensional structure, but now in a different coupling regime. And this higher dimensional structure will also allow us to make a connection with the massive amplitude. So let me be more precise. I will consider a master operator that is given by the infinite sum of all these protected operators. And I will consider only its 4-point function. And we found that this 4-point function of master operators has also an emergent 10-dimensional structure that combines space-time and R-charge distances in a single vector. We further conjecture that the correlator of these master operators in its 10D null limit, it's dual to a massive amplitude in the Coulomb branch. And now the map, a part of trading this position by momenta, we also now recognize that this extra are charge distances mapped to the masses in the dual. Unlike the massless case, we actually don't have a proof of this duality. We in fact also don't have a third object to form a triality. But we have checked this conjecture at very loop orders. And my goal in this talk is to present to you how this 10-dimensional structure arises in a weak coupling, and then to show you how we can use integrability to compute this 10-dimensional null limit and compute a massive amplitude at finite coupling. So the plan for the rest of the talk is as follows. So first I will start in the weak coupling regime, and I will show you that already for the free correlators, there is an emergent 10-dimensional structure. Then I will consider loop corrections by working with suitably defined loop integrands. I will show you that this 10-dimensional structure gets promoted now to a 10D symmetry for the case of the integrands. And after having this experience, I will consider the 10D null limit, and I will sharpen the duality, but now stating that the massive amplitude in the Coulomb branch is equal to a correlator of large charge operators that are known as octagon in the integrability literature. Then I will use integrability to compute this octagon or massive amplitude at finite coupling, and I will also analyze the massless limit that goes back to the origin of the Coulomb branch. So let me start with the free theory. In the free theory, when we compute the correlators of these scalar operators, we just do it by big contractions. Here I show you the 2-point function that is given by this propagator to the power to the dimension of the operator, and here a part of the usual propagator. On the numerator we have the R charge distance. We consider the 4-point function of the master operators. Remember that resums all the BPS operators, and that can be computed as an infinite sum of big contractions. Each set of big contractions can be represented as a graph where we have 6 bundles, given the 6 possible connections between the 4 operators, and each bundle contains a certain amount of propagators. And that's represented here in the exponent of the propagator. And this comes with some coefficients that account for the different distinct ways that we have to draw one of these graphs respecting its topology. Unfortunately, in the planar limit that we consider, and considering this normalization of our single traces, these coefficients happen to be, almost all of them happen to be independent of the length of the operators. So for instance, we have topologies like this one, where it doesn't matter how many propagators we have on each of these bundles. This coefficient is just 1. And similarly here, it doesn't matter how many propagators there are, the coefficient is just 2, the 2 coming from the fact that you can swap these 2 diagonals from inside and outside. Given that property, then it's straightforward to show that this series can be resummed. You identify it as a geometric series, and we obtain a compact expression. And the emergent structure is that now in this compact expression, we have a propagator that gets this correction. The 4D space-time distance is extended, including this 6-dimensional distance. We can now ask if this structure also appears at weak up at loop corrections. So we consider the series expansion in the tooth coupling in the planar limit. And one way to deal with these loop corrections, one efficient way to deal with these loop corrections is by using the Lagrangian insertion method that allows you to define an integrand. This integrand, the L loop integrand, corresponds to a 4+L point correlator that is to be evaluated just at leading order. This correlator contains the 4 external, the original 4 external operators, and also L Lagrangian insertions that we are supposed to integrate over to get the final result. Furthermore, using superconformal symmetry, it's possible to show that this correlator factorizes, and so we can strip out a complicated expression and define an even simpler integrand. There are some advantages of dealing with this integrand, such as the fact that it's a rational function that contains only simple poles. And it also treats, almost treats in the same footing external and integration points. For instance, the integrand of the simplest correlators has a full permutation symmetry that mixes internal and integration points. These integrands, just like in the free theory case, they admit a decomposition in terms of the R charge. But now, instead of the numerical coefficients that we had in the free theory, these get replaced by these functions of the 4D space-time distance. In principle, there should be infinite number of these structures when we consider arbitrarily large R charge. However, in the planar limit and weak coupling at each loop order, there is just a finite basis of inequivalent structures. And this number grows with the loop order. The reason why is that is thanks to some phenomenon that we call saturation, that states that basically on the planar limit, a bridge like this one becomes uncrossable when the number of propagators becomes larger than the loop order. In terms of these structures, that translates into this statement that there is a saturation bound above which we can add any number of propagators on that same bundle without changing the structure. That implies that, that after the saturation bound, there is an infinite tail of coefficients that are identical. So when you try to resum these integrands, there is a similar effect as in the free theory case where you can just take out these identical coefficients, and what you are left with is just a geometric series. Let me give you an example of that. At one loop, the saturation implies that there is only a single structure, which is equal to the integrand of the smallest operators, and it's just given by this product of simple poles. The generic integrand for arbitrary R charge also contains the same structure, dressed with these propagators. These can be taken out of the sum, and what remains can be recognized just as a geometric series. And again, just like in the free theory, we have an emergent 10-dimensional structure for the integrand, for the one loop integrand. There is higher loop data for these structures that we can use to try to find similar patterns. It's more complicated because saturation allows, higher loops allows for more and more structures, but nevertheless, we have found that there is a similar pattern with an emergent 10-dimensional structure. So we conjecture that at each loop order, all these reduced integrands form a geometric series that can be resummed into a function which only depends on this 10-dimensional distance that combines space-time and R charge. From this conjecture, it immediately follows that one way to construct the generating function is by simply uplifting the integrand of the simplest correlators by trading their 4-dimensional dependence to now become 10-dimensional. Following that procedure, we obtain results for the generating functions for various loop orders. Here I present you up to 3 loops. And this generating function, given us the uplift of this seat, it inherits all of its nice properties, such as its full permutation symmetry. This is just not the end of the story, because this is just the integrand and we still have to integrate. And when we integrate, we actually break this 10-dimensional symmetry because we treat the external and internal points in different footing. So for the external points, we consider the BPS condition that states the 6-dimensional vector is null. And for the integration points, we just turn off its 6-dimensional R charge part. And then we integrate over them, also putting back the factor, the SUSY factor we strip out at the beginning. After following that procedure, we obtain results like here. I present examples at up to 2 loops. We obtain the generating function of all 4-point correlators, given in terms of a basis of conformal integrals. In this case, at 2 loops, we just obtain the simple 1 loop and 2 loop ladder integrals. And interestingly, the coefficients of these conformal integrals still carry this part of this 10-dimensional structure, now with this T defined as the propagator. These coefficients carry all the information you need to extract any individual 4-point function. And when we expand it as in a geometric series, we can reproduce all the results for these correlators given in this table. We have performed similar checks up to 5 loops, and then we have predictions at higher loops. These predictions are again just in terms of, well, the coefficients that have 10-dimensional structure and the basis of conformal integrals. However, these conformal integrals are hard to evaluate, so it's still not a final analytic answer for the correlators. Instead of trying to deal with all these family of 4-point functions, we can go to a more tractable problem that considers a subsector of these 4-point functions that corresponds to the correlators with large R charge that we call octagons. Just as a reference, in this table, the last line is full saturation where you just get zeros, and these simplest correlators correspond to the cases where you have some partial saturation and you get various zeros, but still the correlators are non-trivial. So let me tell you about these simplest correlators. These simplest correlators have a large R charge such that we have a frame of infinite R charge, and these are uncrossable, so you cannot draw any of these type of graphs, and you have just a factorization between the inside and outside, the inside square and the outside square. In terms of their integrand, they just receive contributions from these structures where you have infinities for all corresponding to all these edges. And if you go back to our generating function, you can immediately recognize that the only way to produce these terms comes from the terms that contain poles, because these poles are the only ones that, when expanded in a geometric series, can give you arbitrarily infinite R charge. So there is a simple recipe to extract these terms, which would be corresponding to taking this tendinal limit, where you take all these terms going to zero. By doing that, we can show that the tendinal limit gives you all the simplest correlator at once. So here, the simplest correlators are labeled by the finite number of propagators on the diagonals, and we sum over all of them. That gives you the result of the tendinal limit. And as I presented to you in the introduction, this is also equal to a massive amplitude, where now we recognize these 6D distances equal to the masses of this amplitude. We have checked this at the level of the integrand, but this amplitude, because it has some masses, it doesn't suffer from infrared divergences. So this duality that holds at the level of the integrand also carries on at the integrated level. So we have the equality between two infrared finite observables. We don't know how to compute these scattering amplitudes using integrability methods, but we know how to compute these simplest correlators. And well, it goes as follows. So we decompose this octagon in building blocks, where these building blocks have a fixed number of finite propagators in the diagonal. So there are two series accounting for this diagonal or the other one. And each of these building blocks can be computed using the hexagonalization program of this gentleman. So we think of this octagon as a piece of worksheet that we tessellate into two hexagons. And then we glue back the two hexagons by summing over a complete basis of states that live on this two-dimensional worksheet. That gives you an expression for the octagon as an infinite sum of multiparticle states. And unfortunately, this group of people were able to resum that series and provide a more compact answer in terms of a determinant of an infinite matrix. This matrix has a simple way to be described in just a couple of lines. where the elements are given by an integral over Bessel functions and a kernel that contains all the information about the cross ratio. This provides a finite coupling expression for our amplitude, but we haven't been able to yet perform this resummation. Still, this form of the result allows us to study various properties of this octagon amplitude. So let me tell you about them. Our octagon satisfies the Steinman condition that amplitudes are supposed to satisfy. So basically, if you have this amplitude and perform cuts on the S and T channel that overlap, you should get 0. And that, in the case of the octagon, translates as a vanishing double discontinuity. We can also perform the weak coupling expansion, and that gives us an arbitrary loop order, a result in terms of sum of determinants of well-known conformal ladder integrals. And interestingly, we can also compute the strong coupling limit and show that the result exponentiates. And in the exponent, we identify it as the area of a minimal surface in ABS. So here, this would be a representation of the octagon as the 4-point function of large R-charge operators, and you have this minimal surface that ends on these geodesics. We can ask if, by taking the 4D limit, which in terms of the amplitude corresponds to the massless limit, we can ask whether this minimal surface corresponds to a regularization of the minimal surface found by found for the forecast null-Wilson loop. That seems to be the case, but actually in detail, they don't have the same exponents. And there is a way to understand that well, at finite coupling, corresponding to the fact that we identify our amplitude to be a special limit of a more generic Coulomb branch amplitude. A more generic Coulomb branch amplitude has two types of massive particles in the planar limit. You have the external particles, external massive particles, but also you have a loop of this loop in the perimeter is also controlled by massive fields. Starting with this type of Coulomb branch amplitude, it was possible to find our regularized version of the 4-gluon massless amplitude by taking first the limit where the external particles become massless, and then finally when the internal loop becomes massless. So this gives you a Coulomb branch regularized version of the BDS ansatz. On the other hand, our amplitude corresponds to taking the limit in a different order. The result also exponentiates. It's also controlled by a double logarithmic function, but the coefficient is different. Recently, it has been, although these two guys are different, it has been shown that they belong to the same family of functions. They can both be derived from the formed version of the BS equation, the celebrated integrability equation that computes the Cas anomalous dimension. Now, with a deformation for different values of the deformation parameter, you can obtain either the Cas anomalous dimension or our new gamma octagon. There isn't yet an explanation of what is the physical interpretation of this deformation, but in light of our results, we believe that this parameter should be associated to this difference on the order of limits, so possibly related to some ratio of masses in the Coulomb branch. Yes, let me finish with a summary. I have shown you that the generating function of all 4-point functions of protected operators have an emergent 10-dimensional structure, and further, when you take the 10D limit, we make connection with a massive amplitude in the Coulomb branch, which can be computed using integrability. Then there are further questions that we would like to explore in the future. Yes, so let me finish here. Thank you for your attention.
Very much, Frank. Any questions to Frank? I can see that. Carlos?
Hey, Frank. Very nice talk. Just a simple question. Can you explain a little bit more or expand a little the interpretation of alpha as some ratio of masses in the Coulomb branch amplitude?
Actually, I don't have much more to say about it. Just that, so I don't have a prediction for what exactly alpha should be. I just, as I was explaining, I just know that different values of alpha control different limits of this generic Coulomb branch amplitude. So a further analysis of this generic amplitude would allow us to identify what exactly this parameter alpha is, but we haven't performed that.
Nathan?
It was a nice talk. There's a paper about 10 years ago about writing the propagator for scalar superfields in terms of this 10-dimensional language, which looks almost identical to your free propagators. Do you know the relation between them? Is it the same? So they did it in superspace, but if you just take the bosonic part, I think it's just exactly what you have for the free propagator.
Well, I'm not familiar with that result. You're making an analogy with this type of propagator?
Just the first part of your talk, where you wrote down the free propagators. I think even earlier. Yeah, that's construction here. So just the first line, so that you can combine these y's and x's, so you get what you call emergent 10D structure. So it just comes from the conformal invariant. If you take two of these operators, then it's just from the conformal symmetry. You can take the large radius limit, and then it looks like 10 dimensions.
Yeah, so maybe you can give me the reference.
Okay. Yeah, so it's called covariant propagator in ADS5 times S5 superspace. So if you just take the bosonic part of it. So they did the full, you just did the lowest component of the superfield. They did the whole superfield.
Maybe I can briefly comment on this, because that paper also showed up in our supergravity story. So it's true that the ADS5 cross S5 propagator you can rewrite in this 10D conformal form by making conformal transformation. Using that ADS5 cross S5 is conformally flat to 10D flat space. This story is a bit different here because we're not that strong TF coupling. We're at the limit of weak TF coupling, where the bulk interpretation is far less clear.
I understand. I'm just saying these superfields, these things you called OK.
Yes.
That's just dual to the 10-dimensional, to the superfields. So if you just look at the superfields in harmonic superspace, that's just the lowest component to the superfield. So you wrote just the X and Y dependence, but you can actually expand this to all the theta dependence. So that's what they did.
Yes. Do you think that could be done for, maybe let's track the discussion. Other people have questions.
Yeah, thanks.
Ethan?
Hi, Frank, thanks for a nice talk. So I just have a question about this octagon at strong coupling. So you said that at strong coupling, the exponent of the octagon has some relation to the area of the worldsheet. Can you say anything about the string theory side of the story? This is something you have attempted to make more precise?
The result we have only come from integrability. We don't have the counterpart on the string theory side.
So even for some symmetric configuration of the the boundary insertions, you cannot directly compare the area of the worldsheet to this expression?
Yeah, we haven't performed that computation on the
I see. Just want to make sure. So this particular configuration on the worldsheet does not preserve any supersymmetry?
I believe in principle, no, because no, actually, I don't know if it does or not. Well,
so for example, if the insertions correspond to the ground states or correspond to the PPS operators?
So one realization of these polarizations for these large charge operators corresponds to making a specific choice of polarizations.
Yes.
And well, because it doesn't look very symmetric, it seems like you don't preserve much symmetry. But yeah, but I'm not aware actually if there is some.
I see. So you don't expect there to be some kind of integrable this equation that will govern this minimal surface, or just something that you have not tried?
I haven't explored the strong coupling side from the string side. No, I mean I cannot report anything on that.
Okay. Okay. All right. Thank you.
Hiroshi?
Yeah, so I don't work in this area, so I'm afraid my question might be totally off. But I wonder whether there is something like a Mellin transform which takes into account R charges. It seems like the 10-dimensional symmetry naively look like a probing local structure of ADS5 cross S5, and so 10-dimensional version of Mellin transform or something like that might be insightful. So I wonder whether anything known about this kind of ideas?
So in this work, we haven't done that, but I believe maybe Simon in the supergravity side has worked with this Mellin transforms. I don't know if Simon has something to say.
I think it may have been used at strong coupling in a recent paper by Oleslop and collaborators. You can use it when you have an object that is precisely, that satisfies a 10-dimensional conformal symmetry. Here we should be clear that this correlation function here does not satisfy it. Its integrand satisfy it, but once you integrate, it does not. We use the symmetry of the integrand as an intermediate step to justify this 10D null limit. But the correlation function that we're talking about does not enjoy a 10-dimensional conformal symmetry.
Well, let me just mention that there is precisely the paper by Pedro Vieira and Francesco April, which precisely did this Mellin transformation, including R symmetry direction.
Thank you for pointing that out.
Gloria?
Frank, if you start deforming n equals 4 Young Mills, beta deform, gamma deform, would you see, say for beta deformed version, would you see some reduced symmetry, like less dimensional, but more than 4-dimensional? And if so, if you go to the Fishnet limit, would you observe something like this symmetry, higher dimensional symmetry, of course, not 10-dimensional?
Yeah, well, the answer I don't know, but it's true that at least in weak coupling, we see that on the structure of the expansional weak coupling, we actually contain the Fishnet type, the Fishnet graphs that appear on your Fishnet limit. So we can wonder if there is a limit that we can take that allows us to focus only on these Fishnet graphs, and we actually don't have a way to do it yet. But yeah, that could be interesting to explore.
I would think that if you gradually destroy the symmetry group by deformations, it will be less and less of this symmetry, but still there will be some higher dimensional symmetry, yes?
Yeah, well, to begin with, we don't know why there is this 10-dimensional symmetry at the level of the integrand. Mm-hmm. But at least when we consider the correlator of these master operators, we know that we have a chance of maybe having some emergent higher dimensional structure, given that these extra R charge are supposed to account for the kinematics on the internal manifold. So in the beta deformation, probably there should be a similar effect. But I cannot guarantee. Well, even for this theory, I cannot guarantee. I don't have an argument to tell you why the symmetry appears. At the moment, it's just an observation.
Thank you. Also, Juan is asking a question in the chat, which would be interesting for me as well, maybe for other people.
Please, Leonardo.
Yes, we do not understand the symmetry at any deep level. It's broken at finite coupling. It's there as strong coupling and at a weak coupling. It is somehow related to the fact that the bulk background is conformally flat, but making that precise would be nice. So a similar symmetry has been observed, at least a strong coupling in ADS3 times S3, but it's definitely absent in M-theory backgrounds such as ADS7 times S4 or ADS4 times S7, which are not conformally flat. So I think it's an excellent open problem to explain at least a strong coupling more conceptually where this comes from. And it clearly has to be related with the fact that the bulk is conformally flat.
Okay, it seems that there are no more questions. So let's.
Yeah, I guess there is this question: how does the information about the polarizations of the particles in the amplitude appear in the correlation side? Are they stripped out as in the massless case? Yeah, well, the short answer is yes, they are stripped out. But yeah, we haven't worked out the map concretely.
So let's thank Frank again. And, see you all tomorrow.
Thank you.